astronomers have uncovered a new side of the early universe. Using the James Webb Space Telescope, a team from the University of Cambridge studied more than 250 young galaxies and found that most were anything but calm. Instead of structured rotating disks, they were chaotic, clumpy, and turbulent, struggling to stabilize in their first billion years. This discovery reshapes how we understand galaxy formation and early cosmic structure. In this video, we'll explore what Webb revealed, why it matters, and what comes next. Let's get started. To grasp the impact of this discovery, we need to look at what was observed. Roughly 800 million to 1.5 billion years after the Big Bang, galaxies were still in their formative stages. For years, scientists debated whether they settled into rotating disks quickly or developed through a longer, more chaotic process. The Cambridge team used JWST's NIRCam instrument in GRISM mode to analyze more than 250 galaxies from this early period. This mode allowed them to capture faint light from ionized hydrogen and track how gas moves inside each galaxy. It was a large-scale look at galactic dynamics that previous telescopes couldn't deliver. The results were striking. Most galaxies didn't show the smooth rotation we associate with mature systems like the Milky Way. Instead, their gas moved in multiple directions, forming turbulent and irregular structures. Only a small fraction showed early signs of rotation. This is a major shift from earlier studies, which focused on a handful of bright, massive galaxies and gave the impression that ordered disks were common at early times. Those objects were the exceptions. The new, broader sample reveals that the typical early galaxy was messy and unstable. As lead author Lola Dan Have put it, "We don't just see a few spectacular outliers. We looked at an entire population, and most are still chaotic, with gas puffed up and moving in all directions." This is the clearest statistical view we've had of early galactic behavior. It shows that the universe in its first billion years wasn't made up of elegant spirals. It was dominated by dynamic, turbulent systems still trying to settle. Why is this important? Because it provides the strongest evidence yet that galaxy formation in the early universe was a messy, drawn-out process, not an immediate leap into structure. For decades, theoretical models predicted that early galaxies should be unstable, full of gas, and prone to turbulence. Observational evidence, however, was too sparse to confirm it at scale. JWST has now filled that gap. There are three main physical factors driving this chaotic behavior. 1. High gas fractions. Early galaxies were dominated by gas, not stars. Gas-rich systems are easily stirred by disturbances, leading to irregular flows and clumpy structures rather than well-ordered disks. 2. Frequent mergers and bursts of star formation. In the young universe, collisions between galaxies were common. Each merger injected energy, disrupted developing structure, and triggered rapid star formation. That feedback amplified the turbulence. 3rd, gradual disk formation. Only a few galaxies showed signs of rotation. This supports a scenario where stable disks form gradually over time. As galaxies grow in mass, their gas cools, and interactions lessen. Co-author Sandro Takela highlighted that previous work looked at individual standout galaxies, which painted a skewed picture. Examining hundreds of lower mass systems provides a far more realistic view of how galaxies actually behaved during this era. This discovery also bridges two pivotal epochs in cosmic history: the epoch of reionization, when the first galaxies illuminated the universe, and cosmic noon, when star formation peaked. These turbulent galaxies represent the transition phase between those periods, the point when structure was forming but not yet stable. Rather than revising theory, Webb's observations confirm it with unprecedented clarity. Most galaxies weren't born settled. They grew into order through chaos. The implications of this discovery extend far beyond these specific galaxies. 1. Refining galaxy evolution models. Models of galaxy formation will need to account for a longer period of instability in the early universe. The idea that early galaxies quickly spun into orderly disks doesn't hold up statistically. Turbulence, mergers, and feedback were dominant processes for a significant stretch of cosmic time. 2. Expanding observational horizons, JWST's sensitivity, allows astronomers to examine not just a few extraordinary galaxies, but entire populations. This opens the door to studying other properties of the same systems, including cold gas and dust. Combining these datasets will help reveal how turbulence transitions into stability. 3. A glimpse into the Milky Way's past. These galaxies may resemble what the Milky Way looked like in its youth: turbulent, irregular, and undergoing constant change. Studying them is effectively a look back at our own galaxy's formative years. 4. Future research. The next steps involve exploring even earlier epochs, pushing closer to the first few 100 million years after the Big Bang. Researchers also aim to observe galaxies of different masses and environments to understand how and when turbulence fades and ordered rotation takes over. Tchela summed it up clearly. This is just the beginning. With more data, we'll be able to track how these turbulent systems grew up and became the graceful spirals we see today. This discovery redefines our expectations. The early universe was not a serene place of neatly forming galaxies. It was loud, unstable, and incredibly active. The James Webb Space Telescope shows early galaxies were chaotic, not orderly. This confirms that cosmic structure emerged slowly through turbulence and change. It's a glimpse of how galaxies like ours grew from chaos into order.